All right, everyone. Today we are taking on a little introduction to inverses. So this is a topic that is not taught in Algebra 1. This is meant to be a little preview topic for Algebra 2. So graph the inverse of each function, draw in the reflection line. So we're given a quadratic function graphed right here. So it graphs as a parabola. So to find its inverse, we have to swap out the x and y values. So swap the x and y values. So let's say that I look right here at the vertex. That's at -2, 0. So if I switch the x and the y, right, there's the x, there's the y. So if I switch their positions, it becomes 0, -2. So right here. Okay, let's say that I look at this point right here. That's -3, 1. So if I switch the x and the y, it becomes 1, -3. So 1, -3 right here. Okay, this point right here, left 1, up 1. So -1, 1. We swap and it becomes 1, -1 right here. So I'm able to see that my parabola, my upright parabola, it's looking sideways right now. These last 2 points, this was -4, 4. So at 4, -4 right here would be that point. And then right here at 0, 4 becomes 4, 0. Right there, there's that point. So I can see that, oh yes, my upright parabola, its inverse just looks like a sideways parabola, just like so. So this is what the inverse looks like of that original function. Where would be the reflection line? So what would be the line I would have to draw in to make a mirror? So what I should be able to see is that it's going to fall in right here. So I can see that that is my mirror line. That is my line of reflection right there. I can see how it reflects over that line to the other side. So where is that line at? Well, if I look at this point and this point, right here would be right smack in the middle. These 2 points right in the middle would be right here. In between those 2 points would be right here. I can see that I have this line, this very basic line of y equals x. So right there, my mirror line, that reflection line, will be y equals x. Okay, so for a function to have an inverse, all we do is we switch the x and y values. Okay, and then graphically, a good way to eyeball that you have it in the right spot is looking at, did it reflect over y equals x? So let's try that one more time with the second example. This one, I have an absolute value function. If I picture where its reflection is going to be, right, I can picture it kind of right in here, just like that. But let's still find it the same way. So we know, again, that we swap the x and y values. So this point right here, that vertex is at 0, 3, which will become 3, 0. Right there. Okay, this point right here is -1, 4, which will become 4, -1. Okay, this point right here is 1, 4, which will become 4, 1. Right there. So now I can see exactly where those other points would fall. I'd have a point here and here. Here and here. And then here we go. So I can see my inverse right there in red. And then if I draw in my line of symmetry, my mirror line, starting at the origin, up 1, right 1, up 1, right 1, here would be my mirror at y equals x. That is my reflection line. Okay, so again, if we are given a graph and we want to find the inverse, we literally just swap the x and y values. We know that we should have a reflection over the line y equals x. Okay, in example 2, we're going to find the inverse of each function, and then we're going to graph both on the same coordinate plane. So now we have to use some algebra to be able to find the inverse. So in my first example, here I have f of x equals 2x minus 6. So what that is that's a line in function notation. So this reads as f of x. What's the value, the y value of your function for a certain x value? That's what that reads as. So I can just rewrite it as y equals 2x minus 6. That would be perfectly fine, right? That's really the same equation, it's just in a different notation. So if I go ahead and graph that one to start, I'll graph it in red. I know that that's slope-intercept form, so I'm going down 6 right here. And then I'm going up to right 1, up to right 1, and so forth. So I'm just giving myself a lot of points just to see my line clearly. So here is my original line, right? It's a linear function, just like so. Okay, let's derive the inverse. So just like before, we have to swap the x and y values. So swap x and y values. So x equals 2y minus 6. Okay, and now I have to resolve my equation for the y. So I'm going to add the 6 over to the other side. X plus 6 equals 2y. Okay, I'm trying to get that y all by itself. So I want to divide each term by 2. So now I have y equals x over 2 plus 3. And whenever I have x over 2, right, that's really the same thing as saying 1/2 of x. So I'm actually going to take the time to write it like that too. It's a little bit easier to graph and see in that structure. So I could leave it like that. My inverse is also a line. Y equals 1/2 x plus 3. I could also use my fancy inverse notation and say inverse of function f like this. Kind of looks like an exponent, but it reads as inverse. So inverse of function f of x is equal to 1/2 of x plus 3. So I've derived my inverse, and now I want to graph it. So I'm going up 3, right? It's in slope-intercept form. So there's my y-intercept at 3, and then I know that my slope is 1/2. So up 1, right 2. Up 1, right 2, up 1, right 2, up 1, right 2. There we go. So here is my inverse. So the inverse of a line is still a line. It looks like that in purple. Okay, and then just to verify it visually, I'm going to draw in the line y equals x. So here I'm at the origin. Up 1, right 1, like so. So I just want to draw that in and verify that it's a true reflection line, a true mirror line. And it looks great. Okay, so just another way for me to double check that it did actually reflect across that line, y equals x. Okay, next up, same deal. For problem B, here I see that I'm starting with a quadratic function. And if I rewrite it, I can write it as y equals x squared plus 2. So it's a quadratic function, right? It's just translated up 2 units. So I'm going to go ahead and graph it up 2 units. Here we go. And then over 1, up 1, back to the vertex, over 2, up 4. On both sides. All right, so there is my quadratic function, g of x, or y equals x squared plus 2. So if I picture where its inverse is going to fall, it's going to fall kind of like this. It's going to be a sideways parabola, just like we saw in that very first problem. Okay, so here I have to derive it. So let me swap the x and y values. X equals y squared plus 2. Okay, I'm trying to solve for y, so I'm going to take away the 2. So x minus 2 equals y squared. Still trying to solve for y, so I want to unlock the square by taking the square root of each side. And y equals plus or minus the square root of x minus 2. So here, I'm actually not going to use my fancy inverse notation because this is actually two separate functions. I have this one, square root of x minus 2, and a negative 1 times the square root of x minus 2. So my inverse is really two separate functions. It's going to be a square root function, 2 to the right, and then its reflection. So if I go over 2 to the right, right there, and I graph my positive square root of x minus 2, over 1, up 1, over 4, and up 2, right there, that would be the positive, right there, positive square root of x minus 2, and then I need its reflection. So here I just need to make sure it opens down, right? I need to make sure it's reflecting over the x-axis. So over 1, down 1, over 4, and down 2. So again, it's just important to notice that these are two separate square root functions. That was the positive, that was the negative. Okay, and if I draw in my reflection line, I'm at the origin, up 1, right 1, up 1, right 1, and so forth. Right, I'm just making sure that I graphed it appropriately. So I'm just checking to make sure that this line is y equals x, and that that's a true mirror line, that reflection line. Okay, one more. So here in C, now I have h of x. So again, that's just function notation. That would be the same as y equals x minus 1 is a quantity cubed. So if I graph that, that's my cubic function, but 1 unit to the right. So instead of being at the origin, I'm 1 over, right there. And then from here, I go over 1, up 1. And I go back to that starting point, left 1, down 1. Go back to where we started right here at 1, 0. Okay, my next batch of points, I'm going to go right 2 and then up 8, because that's 2 cubed. So up 8 puts me right here. Okay, back to that starting point. I'm going to go left 2 and down 8, because it's negative 2 cubed, which is negative 8, right there. So here is my original function, function h. All right, so now I need to derive its inverse. So here I need to swap the x and y values. So x equals y minus 1 cubed. So here, to get to my y, I have to unlock that cube, that exponent of 3. So I'm going to take the cube root of each side. So now I have the cube root of x is equal to y minus 1. And then the last thing to do is to add the 1 over to the other side. So y equals the cube root of x, and then add 1. So then I can use my fancy function notation for the inverse. So the inverse of function h of x is equal to the cube root of x plus 1. Okay, so now we're seeing a new function. We actually haven't seen this one yet. So this new function, y equals the cube root of x. It's the inverse of a cubic function of y equals x to the 3rd power. So the way that I graph it, let me make a little sketch so you can see what the parent would look like. So if I use a table, I'm going to insert all of my perfect cubes. So I'm going to insert negative 8, negative 1, 0, 1, and 8. So the cube root of -8 is -2. Cube root of -1, still -1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. So if I was just graphing my parent, I'd have these points, just like I did for the cubic one. But then here I'm going right 8 and up 2, so it'd be about like that. And I'm going left 8 and down 2, so about like that. So the cube root parent function looks kind of like this. All right, so now I have to replicate that, but I'm going 1 unit up. So my starting point is 1 unit up. Okay, so from this starting point, I need to go over 1 and up 1, left 1, down 1. Okay, back to that starting point. Okay, now from here, I'm going to go right 8. So 1, 2, 3, 4, 5, 6, 7, 8, and up 2 right there. Go back to that starting point. I want to go left 8, so here, and down 2 right there. Okay, and then I can connect my dots. And there is my cube root function, but up 1 unit. And then again, I keep wanting to double check that I have a true mirror line. So right here at the origin, up 1, right 1, up 1, right 1. Give myself a few points like that. And then I'm going to draw in my mirror line, my beautiful line of reflection. Okay, so right there we go. Y equals x. So I can see how my cubic function, right, reflects over to be a cube root function as its inverse. So inverses, we can always swap the x and y values. We can also, if we're given an equation, we can derive the inverse, swap the x and y values, and resolve the equation for y. And when we look at it on a graph, we should see that it's a reflection over the line y equals x. All right, have a good rest of your day.